Hey, 12th graders. So we are starting Unit 12, and Unit 12 is going to be about exponential modeling. Exponential modeling is going to be encompassed in a lot of different ways. We're going to first talk about it with geometric sequences and series. We're going to talk about it when we discuss just like what does an exponential model in general look like. And then we'll also talk about it with regards to financial algebra and how do we solve for interest and annuity and amortization. So there's going to be a lot of stuff that's going to be encompassed in this unit, but it's all going to be under the umbrella of exponential modeling because they are all exponential models. Now, we have talked about sequences and series in the past, and a quick little refresh. What we have talked about is arithmetic or arithmetic. Sorry, I always say that wrong. Sequences and series. And if you remember with arithmetic sequences and series, it's always repeated addition. Whereas geometric sequences, we will talk about today, is repeated multiplication. So, for example, an arithmetic sequence could be something like 3, 8, 13, 18, yada, yada, yada. And we talk about the first term. The first term is very important, and we call it either A sub 1 or U sub 1, and that's our first term. Sometimes we used U sub 0, depending on what we wanted this notation to mean, and sometimes that was something that was a little bit tricky for us in the past. But we'll talk about it as U sub 1 today. And our first term is 3 in this sequence. And then we talked about D, and D was our common difference, and it's the number that you are adding every single time. So in this case, it's 5. If the sequence was getting smaller, your common difference would be a negative number because you're getting smaller by subtracting that out. And then you would have a expression which encompassed, or like a formula that encompassed all of those terms that you could find like the 30th term in the sequence. And that is U sub 1 plus n minus 1 times D in your formula packet. And so in this case, it would be 3 plus n minus 1 times 5. N is kind of like our x, right? And U sub n is kind of like f of x, or our y value. So that's kind of that relationship that we established there. Now, a series is just like a sequence, except for one big difference, which is instead of a comma in between, there's a plus. And we only ever in this class talk about finite geometric and arithmetic series. In other words, it stops, right? S sub 4. You could talk about infinite and what happens if you add these numbers for forever and ever and ever and ever, and what happens. Sometimes it's infinity, but also sometimes it like goes down to a very specific number, which is really interesting, but we don't talk about it in this class. This is where we brought in the sigma notation, the sum of. We could say that S sub 4 is the sum of the first 4 terms, and that goes from the first term to the 4th term of our formula. We could say U sub I, or we could actually write out that equation. And we also have a formula for that, which was in your formula packet, n over 2 times U sub 1 plus U sub n, which in this case, n is the number of terms that we're adding, 4 over 2 times the first term plus the last term. 21 times 2 is 42. Very quick refresh. If this is super stressful for you right now, that's okay. As long as what you got from this is that like, okay, we had this thing where we had a sequence, and the difference between a sequence and then the series is that we added them. There were formulas. They're in my formula packet. That's the general idea I want you to take away from this. We might have to refresh some arithmetic things on our own. Okay. So a geometric sequence is repeated multiplication. So an example of a geometric sequence would be like 2, 4, 8, 16, da-dum, da-dum, da-dum. We still have this notation, U sub 1. U sub 1 is the first term. We could also use u sub 0, but our formulas that we use with that will change a little bit, just like with the arithmetic sequences in series. So I would maybe discourage you from doing that right away, and wait till you get a little bit more comfortable with this before you start playing around with using u sub 0. But it's our first term, and in this case, it's 2. Instead of a D for our common difference, we use the letter R, and the letter R represents our common ratio. It's the number that we repeatedly multiply by. So this is called the common ratio. And it's the repeated multiplier. And in this case, in order to go from 2 to 4, 4 to 8, 8 to 16, we had to multiply by 2. If it was getting smaller, it would be a fraction, right? Like if it was going down by, like if it was 16 and then 8 and then 4 and then 2, that would be a half, right? So since this is over 1, it's getting bigger in the sequence, and that all makes sense. We also have a formula for our geometric sequences, also in your formula packet. It's u sub n equals u sub 1 times r to the n minus 1. Remember that our n is our input, right? Like our x value. And then u sub n is kind of like f of x. So there will be a number for this guy, and there will be a number for this guy, is what it should be. And then n is kind of like our x. That n minus 1, that exponent right here, is only applied to r. So please remember that, right? Like this guy is not applied to u sub 1, only to the r. And then we multiply by u sub 1 afterwards. So a few things with order of operations to keep in mind. All right, example 1. Let's just practice what it's like basically, and then we'll start getting into like a little bit more applied problems. So for each of these geometric sequences, we're going to write down the first term, the common ratio, and then we're going to find the 10th term. First term, pretty easy. It's 2, right? Our common ratio, you have to figure out what would I multiply from 2 to get to 6, 6 to get to 18, 18 to get to 54. It's pretty easy to be able to spot in this problem, but if it gets a little bit more difficult later on, just take a term and divide it by the term that's in front of it, right? If it was 1854, like if it started off on numbers that are a little bit harder to tell, you can just divide a term by the term right before it, and it'll get you what your common ratio is. Always pause and think, does this make sense? I'm getting bigger, so the number should be a number that makes it get bigger and not a number that makes it get smaller, right? If I did 18 divided by 54, I would have gotten 1/3, which doesn't make sense because I know that I'm getting bigger. So just always pause, assess, does this make sense? Even in the middle of your problem, right? Okay, 3, yeah, okay, good, that makes sense, I'm getting bigger. If it was 1/3, all I would need to do is flip that fraction upside down and it would get me the correct ratio. So if you did it upside down, it just flip it and you're good. Okay, so then from here, we just find our 10th term, which we use our formula that's up here, u sub 1 times r to the n minus 1. N in this case is 10. Notice that like mirror, right? That if this is 10, then this is 10, yeah? So that's really just saying 3 to the 9th power, right? I'm putting this outside of the parentheses for a very specific reason, which I'll talk about in part B. And so I would encourage you to always put that exponent outside of the parentheses. And then just always remember that 3 is to the 9th power, not 2. So 3 to the 9th power is some big number, and then we multiply by 2 and it gets even bigger. And our answer is 39,366. Cool. Part B. B is super interesting, and it's why parentheses really matter. We notice here a couple of things. We can pull out our u sub 1, pretty easy. It's just that first term, okay? Now R is a little bit interesting. Something that you might notice in part B is it flips from a negative to a positive to a negative to a positive, and it's going to keep flipping like that back and forth. And this is because our R is a negative value. So every time we multiply by a negative, it switches the sign. So it's a negative value. So I can automatically, when I see flipping signs, I'm going to chunk up my process into smaller pieces. If I discover something, oh, the sign's flipping, that means R must be negative. I just write down negative, And then I can move on. Okay, it's negative what? What number would get me from, ignore the negatives now, 3 to 6 to 12 to 24. Notice how I'm like separating out two parts of that thought process and dealing with them one at a time, right? This is a process that you can use when you're feeling a little bit overwhelmed with like, wait, I don't know what to do. Try to separate things out, and as you figure something out, write it on your page. So now you can just be like, oh, it's just 2, but it's -2 because it keeps switching that sign back and forth. Okay. So then this is why when we do u sub 10 equals u sub 1 times our r to the 10 minus 1. You have to make sure, because of these negative r values, that you put that -2 in parentheses when you raise it to the 9th power, right? That's important. I want you to practice putting this into your calculator correctly. So I'm going to have this be the first question I ask you to do on your own. Okay, you should get positive 1,536, right? Raising this -2 to an odd power made it negative, but then we multiplied by -3 again, a negative again, so then it eventually turned back into positive. Okay, I want you to actually do part C, this last guy, all on your own. U sub 1, 16r. Here you might have noticed that it's getting smaller. So as we talked about earlier, if you feel confused on what to do for r, you can always just take a term, any term in the sequence, and divide it by the term in front of it. 4 over 8. If you simplify that down, maybe you saw this right away and you're like, oh, it's just a half, right? I'm having it every time. Maybe you said 0.5, totally fine. But if this is something that stumps you, or in the future, you might imagine that like if r was 1/5, you might be like, I would not have figured that out. Well, you can always just take a term, divide it by its previous term, and you're good. So r is a half. Finding u sub 10. It's 0.03125. If you left it in fraction form, awesome. That would be 1 over 32. All right, basic ideas of what's going on with geometric sequences. And let's now convert it into what our class talks about, which is the applied version of geometric sequences. So Laura is starting a new job. She earns 48,000 euro in her first year, and her salary increases by 5% each year. Whenever you see a percentage change, that means geometric sequence or series when we get there. So every time you see that there's a consistent change by a percentage, automatically alarm bells go off and you say, that's geometric. Cool. I'm going to highlight that. We're going to underline it, circle it, write geometric. That's the strategy there. So it says first show that her annual salary follows a geometric sequence and state the common ratio. So let's think about this. I'm going to make just a list of values. I'm going to notice the pattern by creating example numbers to the side, a strategy you can do for yourself on a test. So year 1 would be 48,000. Okay. Year 2. Well, it's 5% more each year. So first I would find what is 5% of 48,000, and then I would just add that back on to 48,000. I don't know why I put parentheses there. It just looks nicer. Okay. I'm going to do a little math magic here, and I'm going to factor out the greatest common factor between these two terms, term 1, term 2. The greatest common factor is 48,000. And what am I left with? Well, I'm left with 0.05 plus, and while yes, I'm left with nothing here, I really divided this by itself, and dividing a number by itself is just 1. So by taking out the greatest common factor, it's a little bit easier to see how this would be a geometric sequence. You could stop here and say, this is